So I think I had read that. So you're studying Titan specifically right now. Is that correct? Okay, and you do mostly like what's happening in the atmosphere of Titan.
Yeah, so I mean, my research group studies a lot of different places. We're doing a lot of work on extrasolar planets right now, but
Okay.
Titan's kind of the um, first thing that I loved. I think the story with the clouds. I think I was 19 when I started working on that project.
Okay.
Um, so I've been studying Titan for almost 20 years. Um, and for the most part, I'm interested in the chemistry that's happening in its atmosphere, which is true actually of most of the places that I study and that my research group studies. That's what we're
Mhm.
particularly interested in. More recently, we've also been become interested in trying to understand the interactions between the atmosphere and the surface. And the main reason for that is that there's chemistry going on in the atmosphere that makes a lot of complicated organic molecules, and those molecules end up on the surface eventually as solids. And then, they're carved by all kinds of surface processes. So there's rivers and streams of methane and some other molecules like ethane. There's big dune fields where the sand particles are probably made of organics that were made in the atmosphere. And so as time has gone on, we've also gotten interested in trying to understand more about how the atmosphere and surface interact. Sorry if I seem distracted. My computer has suddenly decided that it's very unhappy, and so I'm trying to close any like rogue programs because my
Processor's
ah
gotten unhappy.
yes,
That's
apparently
okay.
apparently PowerPoint has made it like very very angry, but I think I just managed to force quit PowerPoint, so hopefully that will
PowerPoint's
solve
hogging
the.
all the resources.
Well, the
Um,
problem is this computer is 5.5 years old, and it has been telling me the battery needs to be replaced for 2 years, which is probably fine. And so, like I said, trying to make sure that we squeeze everything we can out of every
right. It's
dollar.
not new upgrades every year. It's
No, certainly not.
making use of old technology. But that's, I mean, I do the same thing.
Okay, I've closed literally every program except for Skype, so hopefully now it will not be so bad. Okay, let's see if that helps.
I mean, it's fine on my end, so we'll see.
Yeah,
So the one thing I was wondering about is, and this is something I'm kind of interested in space things in general, is just like you're talking about studying organic compounds in the atmosphere that's formed in the atmosphere of Titan that descend to the surface. I'm assuming we're not taking physical samples that are coming back here to Earth for you to analyze. So like, how do you determine what those things are, or kind of sort through, what the composition of, I guess, chemicals and compounds that you're looking at actually is?
yeah. So we use a lot of different tools as planetary scientists. So obviously, I mentioned telescopes before, and
Mhm.
so one of the ways that you can study the composition of an atmosphere is with a telescope. And the reason for that is because um, every molecule has like a different fingerprint of the way that it interacts with light.
Okay.
And so if we look at the way sunlight, we know what the sun looks like.
Right.
And so if sunlight is filtered through Titan's atmosphere and we see it on the other side, um, we can then see that imprint of Titan's atmosphere and look for those different fingerprints that we know. So that's one thing that we can do.
Okay.
And that's how, right now, that's how we are learning about the atmospheres of planets around other stars, so extrasolar planets, is
Okay.
by looking at this imprint. We also use spacecraft in the solar system only so far. Maybe someday we'll send a spacecraft to a planet around another star, but right now we're only in the solar system. When we send spacecraft, they do lots of different things. So they can do the same thing that I just mentioned. They'll have instruments on the spacecraft that can study the way that light interacts with an atmosphere or a surface and help us
Hmm.
figure out what it's made out of. Um, but we can also send instruments that will actually directly sample the atmosphere and measure the composition and send that data back to us. And we've done that for Titan with 2 different spacecraft. So the Cassini-Huygens mission was in orbit around Saturn for about 13 years. 13
Hmm.
years? Yeah, that maths. Um, and so Cassini was an orbiter, Huygens was a probe. The Huygens probe descended through Titan's atmosphere, taking samples on the way down.
Hmm.
And so it directly measured the composition of the atmosphere and sent
Okay.
that data back. And then the Cassini orbiter also had an instrument that could ingest Titan's atmosphere. And so even though Cassini was in orbit around Saturn, not Titan, it would occasionally fly by Titan, and often when it did that, it would get close enough that it would fly through the atmosphere
Hmm.
and take samples and measure the composition. So um, we got information that way. And then, so, those are our kind of 2 observational tools where we can, get actual data from the places. But then the other 2 things that we use to study planets in general and Titan's atmosphere specifically, one tool that's really helpful for us are computer models, which I had
Hmm.
mentioned before. And so one of the things that we use to understand the chemistry in Titan's atmosphere are these sophisticated computer models that have like, every possible chemical reaction you could think of and all of the
Okay.
different things that we think are in Titan's atmosphere. And so we can try to understand what kinds of chemistry is happening there, um, and learn from things that way. And then the other tool that we have in our toolbox, which is something that I use a lot, um, are laboratory experiments. And so one of the things that we can do is, we can use that information that we have from the place that we have some data. So either from the telescopes or from, in the case of Titan, from Cassini-Huygens. Um, and then we can try to do laboratory experiments to understand the chemistry. So in my lab at Hopkins, one of the things that we do is we will take those gases that we know, exactly how much there is because we measured it with Cassini.
Right.
And so Titan's atmosphere has methane, like I mentioned before. The other main gas in Titan's atmosphere is nitrogen, just like Earth. And so we'll put methane and nitrogen into a vacuum chamber,
Hmm.
and we expose those gases to some type of energy. Sometimes we'll use light to kind of mimic the sun.
Hmm.
Sometimes we use an energetic plasma to mimic some other processes that happen in atmospheres. But in either case, they break up some of that methane and some of that nitrogen
Hmm.
and start the kinds of chemical reactions that also happen in the atmosphere of Titan or the atmosphere of Venus or wherever.
Okay.
And then we can look at the new gases that are made and figure out what they are. Sometimes these experiments will result in the creation of solid particles, like I mentioned for Titan, that we have created there. And so then we can take that material that gets made in the experiment and we can study its composition. We actually use it for a lot of other things now. So, having gotten interested in trying to understand these surface processes, I just had a graduate student, Shinting Yu, who finished her PhD earlier this year, who got really interested in trying to understand the mechanical properties of this material. So, like,
Hmm.
how hard is it? How easily does it fracture?
Hmm.
Is it brittle? Is it squishy? And then also try to understand the interparticle forces. So, like, is this stuff like, will this stuff get statically charged really easy and then stick to other particles? Is it just kind of sticky on its own and will stick to itself and other things? And so um, we can't do that with the materials on Titan yet because we've never sent a mission there that had the ability to do those types of measurements. But we
Hmm.
use this analog material in the lab to try to at least get an idea of what those properties might be like.
Hmm.
And then people who are trying to model how dunes form on the surface, or whether or not the lakes and seas will have some of these organic particles on the surface, or whether they'll have sunk to the bottom, like have some type of numbers to put into their models or the
Hmm.
calculations that they're doing, because otherwise it just makes stuff up.
Right.
So even though laboratory analogs aren't going to be a perfect analog of the material, until we actually, have a chance to go and really understand those materials better, this is the next best thing that we can do.
Right. It gives you something to instead of just like taking a stab in the complete dark. It gives you something to work off of, and then probably some kind of margin of error where you're like, okay, it almost behaves like we think it should. What if we adjust it by, whatever figure? Is that
Yeah.
kind of the idea?
Yeah, basically.
I was thinking about you're talking about. I think you mentioned trying to study the atmospheres of like exoplanets,
Hmm.
and so with Cassini, obviously we got the Huygens probe physical data from collection on Titan, but the exoplanets, we're not just launching satellites to every single celestial body.
Right.
So um, you were mentioning using basically light passing through the atmosphere and then looking for that fingerprint. I
Hmm.
was wondering if basically the resolution or the sensitivity of the telescopes or receiving objects used affects the quality of the data, because I'm just thinking about like if the light comes through and like say you're like I just have this is impossible, but just go with me for my sort of absurd example. Say I have like my backyard telescope and I'm looking. Well, clearly I'm not going to be able to distinguish anything,
Right.
but then you go to the complete other spectrum and say you could sit on Earth and then look down to you actually use a telescope and look at the size of a molecule. Well, then you have way more information. So I was thinking, I don't know where on that spectrum our instruments are, but I thought it would probably affect the data depending on how far along, how sophisticated those instruments are.
Yeah. So, I mean, the size of the telescope is a big deal, and I mean, there's lots of different things that go into all of this, right? Because the light that's coming from these stars and these planets that are far away, right? It's spreading out like um, as a sphere around
Mm-hmm.
the body, and so the farther away you are, the surface of the sphere has gotten bigger and bigger and bigger, right? So there's
Mm-hmm.
there's less and less light.
Right.
It's actually making it to you as the observer the farther away you are. So one of the things is that really affects the data quality is simply how close we are to that
Yeah.
particular star or planet. It matters what kind of star it is because that affects how much light there is. And
Mm-hmm.
then the size of the telescope matters because that's our collecting area for collecting that light. And so a tiny telescope can only collect a little bit of the light. A bigger telescope can collect a bigger amount. The other issue that we have, depending on what kind of light we want to look at, is that Earth's atmosphere also has a fingerprint.
Mm-hmm.
And so when a telescope is sitting on the ground, um, all of the atmosphere gets in the way because it absorbs a lot of that light. And so it can be really challenging, basically, to look for any molecule that is in Earth's atmosphere
Mm-hmm.
because we already have that fingerprint on the light that's coming.
Right.
So this is one of the reasons why we build telescopes in space, because then they're above Earth's atmosphere. And so we don't have to worry about that fingerprint that Earth's atmosphere is putting on it. And so, but then that becomes challenging because it's much easier to build a big telescope on the ground than it is to build a big telescope in space.
Right.
Um, and so there's lots of different trade-offs, but um, right now we have a couple of really great telescopes in space. We're getting ready to hopefully launch another one in about a year and a half called the James Webb Space Telescope,
Mm-hmm.
which is an absolutely massive telescope that is going to really revolutionize all kinds of astronomy, but it will be very good for trying to measure the composition of um, planetary atmospheres. But meanwhile, here on Earth, people are building new telescopes on the ground. They're building new instruments that have higher spectral resolution, so trying to look at all of those different wavelengths of light.
Mm-hmm.
Um, the better the resolution is there, the more finely we can look at each different kind of photon, the
Okay.
easier it is to correct for Earth's atmosphere, for example, the easier it is to identify other molecules. And so um, there's a lot of things, I think, technologically that weren't possible, 10 years that are possible now. There's going to be a lot of things possible in 10 more years that aren't possible now. And I think it's really exciting time to, I guess, even just, even be a space enthusiast because the field of extrasolar planets is very young.
Hmm.
The first one was discovered in the mid 90s. We now know that there's more than 4,000 planets that we have identified outside of our solar system. We also now know that at least in our galaxy, there are more planets than stars.
Hmm.
Um, so there's a lot of planets, and people are coming up with really clever ways to study them. And so right now, the main way that we study extrasolar planets is using something called a transit method. And so what happens is we have systems where if this is the star and we have the observer, so you're the observer right now.
Okay.
This is going to be very confusing for people who don't watch the video. So
It's just all just all the audio.
that's about to happen right now. I will try to explain it as well.
Get on
But
YouTube, watch the video, it'll make it easier.
we have we have the star, right? And so what happens is that the the planet will go between the observer and the star. So the planet will go in front of the star. And
Okay.
when it does that, it gets in the way of just a little bit of the starlight. So a
Right.
little bit of that star's light won't come to us anymore, or at least it won't come to us unfiltered. And so we look at how that planet affects the starlight. That helps us figure out how big the planet is.
Hmm.
And if the planet has an atmosphere, its atmosphere can put that additional fingerprint of those gases onto the light that comes from the star. And
Right.
so we know what the star looks like because we looked at it without the planet. And then we know what the star plus the planet looks like. And so we can subtract out the signature of the star so that we only see the planet. This is a technique that has been advancing a ton in the past few years,
Hmm.
and people are doing all kinds of really clever things. They can measure day-night temperature variations on these planets using this
Hmm.
technique. We're getting atmospheric composition measurements. People can tell if there's clouds in these atmospheres. And so that's one thing that is really exciting. And these planets are going to be things that will be really good targets for the James Webb Space Telescope. And so we're really excited about what these measurements are going to look like because they're going to give us a lot more insight into the composition of these planets, and we'll really start to be able to at least think about how to search for life, looking at the atmospheric composition
Hmm.
for these planets. Right now, um, we would be pretty hard pressed to use any of the currently existing telescopes to convince ourselves that we have found the evidence of life if we found a place that looked interesting. Uh,
Hmm.
but that may change very soon, which I think is really exciting.
Yeah, I've got. We'll have to back up a little bit and then continue forward. But so I apologize for not knowing, but the with the James Webb Telescope, is it going to sit like in synchronous orbit around Earth, or where? How does that operate once it's in space?
It is going to one of the Lagrange points, which is like a stable spot like that's set up by the gravitational interactions of the Earth and the Sun, and I always forget
Okay.
which Lagrange point it's going to be going to. Um, so it the main important thing about that story is that unlike Hubble, which is in orbit around Earth,
Hmm.
um, James Webb can't be serviced. So we sent astronauts to Hubble a bunch of times,
Hmm.
originally to fix an issue with the mirror, later to put new instruments and
Right.
new gyroscopes and new all these things. And so this is one of the reasons why Hubble has lasted for so
Right.
long. Hubble is 25 or 26 years old,
Hmm.
26 years old, which is bananas because it was
It
definitely not
wasn't supposed
supposed
to
to
last
last,
that
last
long.
that long
Yeah.
at all. And one of the reasons for that, and for all of the amazing science that it's been able to do, is because of those servicing missions. And I think for sure the entire astronomy community is so grateful for those astronauts that risked their lives to service Hubble, because if they hadn't, we probably wouldn't still have Hubble around during this kind of explosion of studying exoplanets.
Hmm.
And Hubble has been one of the really groundbreaking tools for trying to study these planets, because of this issue with Earth's atmosphere getting in the way. And so, hopefully, I'm like looking around and I'm just realizing I have wood like directly behind me. One of the things that we're really hoping for is that Hubble will continue to function really well, so that when James Webb is launched and gets to its orbit and starts taking data, which will take it about 6 months,
Hmm.
um, that will actually have both of them operating at the same time.
Hmm.
There's some really cool synergistic science that we can do if we have both of them functional at the same time. And so I know I definitely speak for the entire astronomy community that we just keep hoping that Hubble just keeps chugging along the way it has been,
Hmm.
um, because of course we can't service it now. So the last Hubble servicing mission was about a decade ago, because we need the space shuttle to service it, and we don't have a space shuttle anymore.
Yeah.
So it's just kind of up there on its own, and fingers crossed it keeps doing that for as long as humanly possible. Or I guess
Yeah.
as long as telescopically possible. I'm not really sure how to refer to Hubble, but
So something like that.